In this video, we want to review some concepts about regression and then go a little bit further and talk about how these questions could be asked in the AP exam. So first, I'm going to make a scatter plot on the calculator and analyze using DOFs. So just a quick reminder, you would put these things in list 1 and list 2. This is data about the miles away from school and the minutes it took to get there. You put this in list 1 and list 2. You'd make a scatter plot. Remember to use Zoom Stat to get a nice graph that fits all of your data. Let me show you what it would look like. So here's my scatter plot from my calculator. So let's just start with the DOFs. D, remember, stands for direction. It looks like it has a positive direction to me. Okay, meaning it's trending up, meaning more miles yields more minutes. O stands for outliers. I do not believe there are any outliers. We certainly have an influential point. We have this one over here, which definitely helps show us that, there's more. Maybe this might be the closest thing to an outlier we have. This person that lives 0.9 miles, but it takes 14 minutes. And I'm guessing that's a person that walks to school. So, we could certainly maybe say none, but if we were going to pick a point, if we had to pick one, it would be 0.914. Because remember, an outlier for this, for DOFs, an outlier means something far away from the trend. So something like this data point way out here, this is not an outlier, because if we drew the line, it would be close to the line. Outliers are points far away from the line. Form. This is where you have to pick. What kind of equation do you think would work? I think it's going to be linear. I think that would work best. Okay, to draw a line through that data like that would probably be best. And finally, the strength. This again is just how well the line fits. So if you draw the line, are most of the points close? I believe they are. So I'm going to say that this is a strong fit. Okay, so it's and certainly now we can put some numbers with that, like correlation. Okay, so that answers DOF. Next, let's find the least squares regression. Okay, so here I went to the stat calc menu. I chose the a plus bx. You can see I have correlation. I have r squared, and again, the correlation 0.86 is very good. Remember, this r squared is the coefficient of determination. This says 76% of all variation in minutes can be explained by by variation in miles. But all this I needed to answer here was, what is the regression equation? So let's use the correct format here. We've got minutes hat is equal to 6.63 plus 0.95 times the number of miles. And finally, interpret the slope. I'm going to put this down here. For each additional mile traveled, it is predicted to increase the time by 0.95 minutes. I apologize for my sloppy writing. Let me just talk about some key components to this. We want to say for each additional mile, we want to talk about this really for 1 mile. For each additional 1 mile, you want to put it in context that for every one explanatory, what's predicted to happen in the response, and that's the other key here is this word predicted. It's a regression equation. It's not going to fit perfectly. What we're predicting will happen is this. Okay, let's answer number 4, the hypothesis test. So we're going to start with a state. Remember, we began that the slope is not, that it is 0. The alternative is that it is not, because we're just testing if a straight line relationship exists. And just make sure you define your parameter. I said that beta is the population slope between the number of miles and minutes. If you recall from our previous video, the plan, I'm going to just say the conditions are all met here. There are 5 things to look for. Was it an independent pieces of data? Was it a simple random sample? Was it linear? Those are 3 things we can all check by just looking at the way the data was collected and our first step, that DOFs. The last 2 pieces of the plan are Are the residuals normally distributed? And is the standard deviation consistent through the entire line, meaning the points don't get further away the longer the line is used? Almost always in problems, you will be told that these conditions are met. You won't have to do them. But maybe look back at a previous video, remember the 5 things: independent, simple random sample, linear set of data, normally distributed residuals, and standard deviation remains the same. Okay? So all conditions are met. The do. Well, we're going to use the linear regression t-test. So I went into my good old test menu. I ran this test for not equal to. The t statistic is with 17 degrees of freedom. Please remember there are 19 pieces of data here. The reason it's 17 degrees of freedom is it takes 2 points to make a line. So we have to do n minus 2. Remember, everything else has been n minus 1. P-value 1.38 times 10 to the negative 6. Let's conclude. We reject the null because the p-value is so low. We have evidence that a linear relationship exists. All right, let's talk a couple more things with linear regression. So what if we wanted to build a confidence interval for the slope? Okay, so build a 90% confidence interval for the slope. Again, the plan would be conditions are met. So how would we do that? Well, first of all, I want you to recall the old formula that is given to you on the AP exam for confidence intervals, which is we use our statistic plus or minus our z or t star and then multiply by the standard error, right? This is found on that formula page. The confidence interval for the slope then is we take the slope we calculated, we do plus or minus the t star, and then multiply that by the standard error for the slope. Okay? So it's really the same kind of formula we've been using for confidence interval for the means or proportions or difference in means and proportions. Ours just happens to be for the slope. Okay? So thinking back to our opening problem with a slope of 0.951, we'd say, all right, so 0.951 plus or minus. Okay, here's that t-chart. So you'd say, all right, 90% confidence. And we scroll up to 17 degrees of freedom. See, 1.740. That is our t-star. So we get it easily with the chart. And then we need the standard error for the slope. And this can be a little bit tricky. Let me show you something. If you recall previously, when we ran the linear regression t-test, we got this menu, right? This value on the bottom, this S right here, this is called the standard error for the line, okay? So 3.45. And what this really is for the residuals. It's a typical residual. Okay. Remember, standard error is kind of this, we never say it's an average, we say it's like a typical difference. This is a typical residual, meaning the distance between the line and the individual points. But that's not the standard error for the slope. So, how do we get the standard error for the slope? Well, there's a very long formula for it. It has to do with residuals. It has to do with the line that we're calculating and correlation. I'm going to show you a shortcut for it using the data we've been given and the data we've calculated. Recall that a t statistic is always a statistic minus a parameter divided by the standard error for that statistic. So let's fill some things in here. Parameter. This is what the number we put in our null. Well, for this test, for the beta test, our null is always 0. Okay? The statistic we're testing is the slope, or b. So this must be the standard error for the slope. So thinking about manipulating this formula, because of course b minus 0 is just b, I could calculate the standard error for my line by doing the slope divided by the t statistic. So I could do 0.951 divided by 7.24. I guess I could go one more decimal to be consistent. And if I do that, that will be my standard error for my slope, just using the data I already have. So 0.13. So 0.131. Okay? But there's also a way, for those that have a TI-84, there is a way to do this in the calculator. It's called linear regression t-interval. Okay? So if you went into your calculator and you found this in the test and you said, I want a 90%, you would get, this is your interval, so we're 90% confident that the slope lands between these two. And it gives you the exact same slope. But this is honestly not something for the AP exam you're going to need to know. Let me show you how this question would be asked in the AP exam. Data show a trend in winning long jump distances for an international competition over those years. Please note, 1972 to 1992 is 21 years. With jumps recorded in inches and dates in years since 1900, the least squares regression line is fit to the data. Computer output is shown below. Okay, so I've got distance hat equals 256.576 plus 0.95893 times the years. Okay? Now, remember, this is your y-intercept data. This is your slope data. Look at all of these pieces. Here's your standard error for your slope. Here's the t-statistic in the beta test. And here's the p-value. Now, I put a little star here. This p-value right here, this is always the not equal to alternative. So if you change this and said, well, it's positive, I want to test the greater than, your p-value would simply be half, right? You just cut your p-value in half if you're only doing one side of it. So make sure you understand that this always represents the not equal to alternative. So if you were going to run this test, you would say, well, there's a t-statistic of 6.81 with 19 degrees of freedom. The p-value is 0.0024, I would reject the null. All of the data you need is right here to run this hypothesis test. And let's say you wanted to make a 95% confidence interval for this. You'd say, all right, my slope was 0.95893 plus or minus. Go to your t-chart, 95% and 19 degrees of freedom, so 2.093, and the standard error for the slope is given to you. It is 0.141. Okay, so that is the way this question is asked on the AP exam, where you're given the data and just need to understand how to use it.